Thank you. So my name is Joey Sparta. I'm from Honeybee Robotics, and I'm going to be talking about sampling the ocean world. So we had a few talks already about drilling down through icy crusts and getting deep into the surface. I'm going to be focusing on sort of sampling the top layer of these icy moons. So I'll talk about the ocean worlds in general and what it might take to sample at the top layer and sort of what the scientific priority is and maybe some engineering challenges that sort of drive the sampling system design itself. Then I'm going to go into the what I'm calling the ISS. This is the actual sampling system that we've put together for the Dragonfly New Frontiers mission. So my colleague Ty Costa and myself were basically started on this project last January, and we've been developing just about every day, working on this sampling system. So pretty fitting that we're here today, and we have an announcement coming today that we're very much anxious and waiting. Then I'm just going to touch on how you can use this for any other ocean world. So this, obviously, for the Dragonfly mission is for Titan, which has an atmosphere. And then I'll touch on how you can use this for airless ocean worlds. So ocean worlds in general, way out in the solar system around gas giants, you have radiation, you have extremely cold temperatures, you have low gravity, and these make for some serious challenges for sampling. In general, the search for life takes us below the surface, so that's why we're drilling down, as everyone in this room is probably aware. But when you start drilling down, and then once you want to actually take that sample and analyze it with an instrument, you've got your instruments are probably in your spacecraft in the warm area, so you've got to get this material from the subsurface into the spacecraft. And in a low gravity environment, you may end up dealing with some really sticky, nasty material, especially on Titan, where you have organics and potential wet, sticky, like sand particles and other things. So essentially, we started on this project and working with Ralph Lorenz, and he handed us a whole bunch of nasty, sticky simulants like sand and oil and wheat flour and just really nasty stuff. And he said, try to figure out how to transport this stuff with using pneumatics, using gas. And so when we designed the system, we thought of four sort of steps or strategies in how we might sample. First, obviously, excavating the surface. So we use a drill to get into the subsurface. And then we transfer that material into the spacecraft. And while we do the transfer, we focus on minimizing crosstalk or cross-contamination, as well as heat transfer. So heat transfer, if we're putting heat into the sample, especially on these icy moons, we're risking losing volatiles or other important signals or aspects of the sample. And then crosstalk, we want to make sure that we're having a clean system that, as we go from sample site to sample site, we're not mixing our signal. And so for this integrated sampling system, we were delivering to two modes of one mass spectrometer. We have a laser desorption and a gas chromatograph, so a GCMS and an LBMS. And it's pretty small volumes, less than a milliliter, and pretty fine particles. And so, like I said, excavating, we use a rotary percussive drill. Drilling is something that Honeybee has done a lot of work with in the past. And sort of the new technology part of this was the pneumatic transport, so using gas to actually carry sample from the ground to the spacecraft. And from a heat transfer standpoint, pneumatics are great. We can use the cold ambient gas that's already on Titan. And so basically the heat transfer is mitigated by the fact that we're operating in the environment, and we've designed our mechanisms to actually operate at the ambient temperature, and so there really isn't much temperature gradient throughout the entire system. Additionally, it's extremely quick. We use a very high airspeed, so like from the time we pull the material out of the ground, it's in a sample cup in less than a tenth of a second. So it's extremely fast, and it is extremely robust, and the fact that the airspeed that we generate is so fast means that it's self-cleaning. And so we don't end up with clogs or sticky like materials sticking to surfaces or other like robotic arms or scoops or other things like that. It's just a very clean system. And it's analogous to like the medical industry, the pharmaceutical industry, where they transport medicines and powders and things like that. They don't want crosstalk. They don't want, they want very fine metered control of fine material. And that's exactly what we're after on this mission and sampling in general. So here's a little diagram that shows what I'm talking about. We've got a drill on the leg of the lander, and this is a rotary percussive drill. And then we put a pneumatic transport system, which can be adapted to icy moons that don't have an atmosphere, which is the later part of this talk. So for the Dragonfly mission for Titan, like I said, it has a nice thick atmosphere, so we can basically do what we do here on Earth. Those of you who have worked in a wood shop, when you're cutting wood and you're done cutting, you might take a shop vacuum and just suction up all the cuttings. That's exactly what we're doing on Dragonfly. We're drilling into the ground, and then we're using a blower, which has a impeller that we spin at a high speed and generate a low pressure. Basically suctions the atmosphere in through a nozzle that's called a pickup foot right here by the drill bit, and it basically lifts the particles up and carries them down the tubing. In our case, we've actually made this even cleaner by diluting the flow. So for every 1 milliliter of sample that we carry, we're carrying 10,000 milliliters of gas with it. So it's extremely diluted, it's extremely clean. We pretty much never had a clog in hundreds of tests that we did. So it's extremely robust. I also mentioned diverter valves. We came up with this component that we added to the system, which allows us to basically have multiple drills and have multiple blowers for redundancy, as well as like drill site diversity. So if you land in a spot and you find something interesting on your left side, you could also sample on the right side and see and compare. You could also have like redundant drills, like you could have multiple drills in case one fails. And you could even have multiple scientific instruments or interfaces. So if you want to have, if you sample something, it looks interesting, maybe you want to hit it with LDMS, and then the next time you might do a GCMS. And I'll just mention that this valve we tested successfully in cryogenic environment. So here's a CONOPS. Deploy the drill from the leg, start drilling, generate some sample, turn on the blower, we'll generate some gas flow, it'll pick up the sample, carry it down the stream, down the tubing here, and then we have a sample cup that Ty actually gave a talk on Monday about, which has been designed to basically extract the particles from the gas flow. And then we just dump the rest of the sample overboard. So here's a video from our testing to show you what this looks like. So we're spinning up the blower here and generating our gas flow. And then we're going to start drilling. So we're rotating, and we're also hammering into the ground to basically break the material into very fine dust. And then this is our pickup foot, which is basically suctioning material every time that drill bit spins all the way up through the system up here, where it's basically captured by this cup. And this cup fills reliably. We fill it up pretty much every time with every simulant that we've tested. So I mentioned earlier the sand oil, the wheat flour, all that, basically the stressing materials that you could try to defeat the system with. It's been successful each time. We tested it at 94 Kelvin in nitrogen gas. So basically as close as we could get to the Titan environment without building an entire Titan chamber with pressure. And we were successful. We tested it with water ice, ammonia water ice, wax and sand, so various actual Titan ice analogs, and we filled our sample cup every time. Then the last part here is talking about how could you use this for Europa Enceladus, any really small body with just vacuum, with no atmosphere. So we've been working on this too at Honeybee. So you basically need to supply your own gas. So you carry a gas tank on board, and then you essentially replace the pickup nozzle with a manifold here. And that allows you to seal against the surface and actually pick material right off of the ground. So here's a close-up of what that looks like. You have a drill that's going to come down, pull material out of the hole, and then you're going to inject gas, which blows the sample downstream. So CONOPS, deploy your drill, come down here into the manifold, generate sample, inject gas, and you're going to blow your gas into the pneumatic tubing just like we do on the Dragonfly. So we brought this into the vacuum. We have a pretty tall vacuum chamber at Honeybee, so we were able to fit some full-scale hardware and basically recreate different planetary surfaces and different like textures and simulants. And so we're successful every time with this too. We tested sandy surfaces, lunar simulants, perhaps a powder surface if you're on a comet, but not Caesar, a rocky surface such as an asteroid, and various other things. So I think it's really cool. I mean, I think this is something that you could probably use with success on most ocean worlds. I mean, right now it seems very promising. The pneumatics are, the pneumatic transfer aspect of this to me is really like the critical technology that enables it. And I think it's a really clean, robust thing that works well for the application. So that's it. We also had a Cold Tech grant, so I wanted to thank NASA for that, as well as the Dragonfly team. And I appreciate your attention. So if there's any questions.
I think we have time for a question.
Steve Ruff, ASU. I'm curious about the blower on the Dragonfly implementation. What's the RPMs on that?
It's about 50,000.
15,000?
50. 50.
50?
Yeah, it's fast. Real fast.
Can you control that? Is there any benefit to be able to slow it down or maybe increase it even?
Yeah, so we are able to control it, and there is a benefit to slowing it down. For example, you can run it at a lower speed to basically have a lower gas flow rate before you sample, which allows you to sort of draw in the atmospheric air and sort of pre-cool everything throughout the system. So that's something we've tested and it works well. But for the testing that we've done, we've just been running this thing to the maximum that we can because we found in our testing that higher airspeed is better, it's cleaner. So.
All right, thanks.